Hello, welcome. My name is Dawn Owens. I am the head of development and commercial markets for Fervo Energy. And I'm here today to give you a whirlwind tour of geothermal energy. I'm going to talk a little bit about the history of geothermal. I'm going to give you some basics and fundamentals that you'll need in order to discuss some of the more interesting and relevant things that are happening in this industry. I'm going to give you an idea of where this resource sits in terms of its size and scalability in the market. And then hopefully we'll also have some time to answer some questions that you may have. We'll watch a fun little video and have a Q&A session at the end. So that's what we're going to do today. Just a little bit about my background. My background is in regulatory economics as well as a master's in business with focus in finance. So the market is really my area of expertise. I've been a geothermal developer for the last 17 years, worked for some of the large independent power producers, and have been with Fervo since employee number 4 for the last 5 years. So I will do my best to moonlight as a geologist or an engineering specifics, but really I will be speaking from the expertise of my company on those elements, and your teaching team actually has put together a lot of great information on these slides in general. So for areas that you're interested in, I highly recommend that you take that presentation off of Canvas and dive into some of the sources. There's a lot of great links if you're interested in going deeper into subjects, because this will again be a very high level overview. Okay, so geothermal to date has been a relatively small part of the energy picture, but it's emerging as an extremely important and fast-growing renewable energy resource. And this first slide describes for you a little bit why. So to date, it's been a niche player because it's been really geographically limited to where it could economically be deployed. But what we're seeing, and actually this is, I think, the third year or second year I've had an opportunity to come and speak with students in the same exact class, taking the same course, and it's still as relevant as ever, but it's growing even faster than I had expected in terms of its importance, not only here in the US on the domestic stage, but also internationally. And so I want to start the lecture by kind of giving you my own thoughts as to why. Why is it becoming a fast-growing resource? And it's actually quite simple to think about here. It's becoming a larger picture of the clean energy transition because we're at a point in time where we are starting to see the nexus of aggressive climate decarbonization goals coming to fruition in markets where at the same time you're having increased energy demand. Okay, and that's the new thing since the last time I gave this lecture, is we're actually, for the first time in history, seeing many markets, not only within the United States, but in a long time, for the first time in recent history, I should say, not in history, but in recent history, last 20 years, of increasing energy demand. Simultaneously, we are decarbonizing our grids, and we are starting to have aggressive policies that will actually help us to support the deployment of 24/7 clean energy. So the slide I'm showing you here on the screen talks about, anecdotally, one of the things I'm talking, just kind of drive this point home. So, we've had for many years, both globally and in the US, we've had RPS goals, Renewable Portfolio Standard goals. We're trying to decarbonize the electric grids. And these goals typically had said we're going to get to 50% carbon reduction date by a certain a time frame. So you can see there that, we used to have 18 states that had these RPS goals. But everyone kind of forgot about the last 30 or 50% until recently. Recently, we've started to see even more companies and states here domestically in the United States and countries stating the same type of goals for 100% decarbonization. Okay, so that's one dynamic that you have going on. You've got regulation and people setting aggressive science-based goals to get to that full 100% decarbonization. At the same time, you have that increasing energy demand, and you have massive deployment of the cheapest economic renewable resources to date, which at the moment are wind and solar. So, kind of moving up to that top left quadrant, you see that as we've had this deployment of the cheapest economic resources, if you're mandated by law to get to a certain decarbonization, and you have to do it, you're going to fill it up with the cheapest resources first. So we're seeing higher and higher deployments of the cheapest resources, wind and solar, and they're inherently intermittent. This point in the quarter, you guys have seen and learned probably lots about that. They're inherently intermittent, and so you're seeing an increased demand for not only renewable energy, but also clean, firm energy, something that can fill the gap when the wind and the solar stop shining. And you're also seeing a deployment of those types of things globally, all over. So one anecdote of why you might be seeing a resurgent or sort of a key example of this dynamics coming into play was the midterm reliability decision here in California. So in California, in June of 2021, the California Public Utilities Commission, looking at all of these dynamics, increasing electric demand, trying to get to 100% carbon renewable, and also strengthening economic or environmental regulation in an attempt to decommission a nuclear facility here in California, Diablo Canyon, said, shoot, we certainly are going to go against our goals if we replace Diablo Canyon with fossil fuels. So we're going to actually mandate for the first time in history that you have to procure, that renewable energy providers need to procure clean, firm power. And at first, the first draft of that legislation actually said geothermal itself. And they walked that back to say, actually, there are other clean, firm power that could do this. But this was the first time that we saw in the market an actual specification of an environmental resource. And it's a really important turning point for geothermal development because this gave a signal to companies like Fervo and others like Sage and others that have now been launched to really deploy resources and time into furthering innovations. So I like to start there just because I think it's a really relevant thing that when you're sitting here in California to know that California in many ways is kind of a really interesting place to be studying this dynamic because they are at the forefront of launching new technologies that are helping to accelerate geothermal development. But geothermal development is actually not new. So I'm getting ahead of myself a little bit. To really understand what something is today and where it's going in the future, it's important to understand where it came from. And geothermal is actually one of the oldest forms of power production that we have. In fact, geothermal has been being used for electricity and other purposes of energy production for as long as humans have been wandering around and noticing that at certain parts places in the earth the water was hot or that there was actual physical steam coming up from vents in the ground. And the first time that geothermal was used in power production was actually in Italy, just outside of Tuscany in a town called Lardello. And the first geothermal plant was actually commissioned and started producing electricity in 1904. And I didn't mention this, but my background, I actually started doing natural gas development. And when I first learned this fact, it kind of blew my mind that a resource that has been being used for electric production for that long could still be sort of in this niche environment. Like, why hasn't it proliferated? Why isn't there this mass deployment of that resources? And my hope is that through the course of this lecture, that's one of the questions that you will have answered, is why it hadn't been launched previously in the past and why it's an exciting time for this resource to be proliferated now. So, okay. This slide, though, if we take a walk through history, can also give us some indication, and we'll go through this more. So very little in the 1900s. Then we started to have a period in the 1960s here in the United States where we started to have a little bit more deployment of geothermal. And, that growth was actually started again here in California with the geysers. The geysers started in the 1960s here, and they're a particular type of geothermal development. But shortly after the geysers came online, people started thinking, well, maybe there is something to this. And there was some legislation that was enacted with PURPA, which was a very key piece of legislation, and highlights another thing that I'd like you to take away from this lecture, which is it's really the intersection of policy, finance, and technology that help a renewable resource be deployed on a wide basis. So with the enactment of PURPA, you started to have a larger deployment. This is also the first time you saw binary technology, which can produce electricity at lower temperatures, be deployed. And then we went into this sort of like dark ages, this geothermal dark ages, where not a whole lot was done. It was kind of like we made these advancements, and then nothing happened, really. Until we started getting into the 2000s, early 2000s, we had a small blip where there was a heavy interest in this when we started seeing really aggressive renewable goals. People started thinking about decarbonization, and many of those projects failed. And the banks and everyone else said, okay, this is clearly a niche resource. It doesn't work. Move on to something else. And that remained the status quo until really the 2022, when Fervo and Advanced Geothermal and EGS started to make inroads again. So that's a quick walk of history. And sometimes you can see this better graphically. For those of you that are graphically, you can kind of see what I'm showing here is just the US power sector, and that you can kind of see that rapid growth in the 1980s and the resurgence here. This is a graph of the total installed geothermal capacity. Again, just a graphical representation of the overall installed capacity to make those points that I was just talking about a little bit more clear. Okay, so now, so far we've looked at, okay, I'm telling you it's important. I'm telling you that in the past it's been here for a long time, but has struggled to really take off. Now let's understand some of the fundamentals so that you can understand even more about why it could be different now than it's been in the past. So we're going to go into some of the origins of geothermal electricity. We're going to talk about the applications and where it's currently deployed, and we're going to go through some of the key principles and resources of extracting that resource. And one important note as we move into this section is that in this lecture, we will only be talking about geothermal as an electrical production. Geothermal can also be used in its direct heat form, either in residential or small applications, but this lecture will focus only on geothermal for electricity production. So let's talk about what the heck is geothermal. I've now stood up here for several minutes, probably too much, and talked all about this, but there may be some of you who this is really a new resource, and you're sitting there going, okay, I've heard of solar, I've heard of wind, I don't know what the heck she's talking about. What is geothermal? Well, geothermal really at its fundamental core is just the heat that's within the earth. And it's actually really interesting because I don't know if any of your other lectures have talked about this, but geothermal and all electricity and energy production can really all be sort of boiled down into some form of nuclear reaction. And geothermal is no different. I like to tell this story, but it's still one of my favorites, which is when I was first entering into the geothermal space, I was digging all in and being like, why is the earth hot? Okay, I knew there was like molten lava, but why? I never understood why. And when I was looking back through it, I realized that it's actually left over. Essentially, geothermal is about 50% left over from when the Earth originally was formed, which is very fascinating to me. And I had this aha moment while I was sitting studying. I'm a single mom, and I was sitting there studying, and I happened to mention this to my, at the time, young child, and he was like, "You mean you developed dinosaur energy, Mom?" Which I thought was like kind of a silly way to put it, but now I still always think about that geothermal really is half dinosaur energy, or essentially primordial heat, meaning when the Earth was originally formed. The other half of that energy source is actually radiogenic heat, which is essentially the nuclear process of elements breaking down. So at its fundamental core, that's how this energy is being created. And when we talk about geothermal and geothermal development, we're really talking about accessing that energy and harnessing and using it for power production. That's what we're talking about today. And in the past, geothermal energy has been pretty geographically limited. On this map, I am showing here in I have to make sure I get the colors right here. So the orange dots here on this map are where existing geothermal that is used for electricity production is located. And the blue dots are where geothermal for direct heat purposes is located. And I said earlier that it's been geographically located not because it's not everywhere, but because that's where we've been able to access it. Okay, so where tectonics happen, and you're right on it, which is essentially, this is where the Earth's pieces of the Earth come together. Please forgive my ridiculously elementary description of geology for any of you who actually have a background in this. But where the Earth comes together, and you can either have pushing or pulling. When you have the pulling, it's thinner. The Earth's crust is thinner in this location, meaning that it's easier to access that resource. And quite simply, all of the orange dots are around the ring of fire where the Earth is closer to the surface, easier for us to access it. And that, to date, has been why it's been limited, because you have to find a place where you can access it at an economically, right? Getting actual to the resource. So let's talk a little bit about that. So just some facts from that map that we saw. So geothermal for direct use, which again, the lecture doesn't completely cover, but its significance, its main growth at this point is in China. It is growing, and it's important to reference that. And also the European Union, there's a big resurgence right now of geothermal for direct heat in those two markets. It is very site-specific, and it's hard to move the heat pretty far, right? If you've been studying energy systems for a while, you know that there's big losses of the heat. So this is one thing that you've been needing to take into account when you're talking about direct heat. For geothermal electricity production, it's less than 2%. I said a couple times in the lecture that it was a small part. We're going to put some numbers around that now. It's less than 1% of the world and less than 2% of the US electric use capacity, installed capacity at the moment. Now, that's a pretty dang small part right now. And it is typically been very limited to site-specific and where it was able to be used. It needed to be used in site. So another important part that we'll talk about here is that geothermal, depending on how you use that Earth's heat to convert it to electricity, can either be a fully renewable resource or a semi-renewable resource in terms of the definition we use. And I'll talk a little bit more about that later, but essentially, you need to ensure that there are no fugitive emissions from the water that you're using. So depending on if you're using flash or binary, which we haven't gotten into that part of the lecture, but it will make more sense, I promise, once we get there. You also have to ensure that you are using and depleting the heat in the same time frame that it can be regenerated. So, we are using a heat source that is half primordial and half radiogenic. And if you use up the heat faster than it can recharge, a geothermal resource can recharge, you will have a decline in the available heat for power production. This actually happened in the geysers, actually. There was a pretty significant drop in the heat because they didn't know about these principles, and they sort of used more and accessed it in a way that it wasn't able to recharge as quick as they were using it. Okay, so talked about it's limited. To understand fully why it's limited and to really get as excited as I and Fervo is about the resurgence of geothermal, you need to understand one more thing about why. So there's three fundamental things that for traditional hydrothermal geothermal that must occur for a geothermal facility to exist. So you have to find a place where all three of these things are and exist in order to have a successful geothermal plant. These three things are: you need the heat from the earth, you need water as a conductive resource because you're going to use that water to actually access the heat, and you need permeable rock. And so you need to be able to access all three of these things in a traditional hydrothermal system in order to have a successful geothermal project. And as we saw in that previous slide, where that was typically available was in the ring of fire, where you had those things. You had water, you had heat, and you had permeable rock so that that water could flow through those rocks to access it. And that is why it was pretty limited. So I do want to give you a quick example for those of you that are engineers or have worked in the oil and gas space. You might recognize this. This is a temperature gradient log. And this is a temperature gradient log of a geothermal reservoir compared to the natural temperature gradient. And essentially you can see that the point of this that I want you to take away without getting too far into details is that in order to access this heat, we have to go thousands and thousands of feet below the Earth's surface. And that typically that is pretty costly to drill. At each foot that you drill is pretty costly. And so just to kind of re-hone on this point, that the reason geothermal was limited around the ring of fire is because that's where the Earth's crust was thinner and where we could access the heat easier. There's lots more we can go into this, and this is one of the points where I'd say check the link because this is actually very interesting, but I will move on in the interest of time because I want to make sure you have time to watch a very fun video. All right, so now you understand the fundamental elements of what you need for geothermal. Let's talk about how we find, or how we have found in the past, that magic trifecta. We're going to talk about exploration methods, a little bit about the types of the geothermal plants so that you can understand my comments on flash versus steam, if you're still going, what the heck is that? And then we're going to talk a little bit about the emerging technologies. Talked about what we need from the subsurface perspective. Now we're going to talk about how we find it and how, once we found it, we convert it to electricity. Okay, so the discovery process for geothermal is very, very similar to the discovery process for hydrocarbons. So if you are, like many Stanford students, and coming into this program because you are interested in transitioning from the oil and gas sector, like Fervo's founders, you may be very familiar with this. Essentially, you can look from the top side of the surface and you can do geology and geophysics and chemistry reviews. You do sort of a topographical analysis through LIDAR or other methods to try and find where you might see potential heat sources. And you sort of start to characterize. And then in phase 2, and really a key element for geothermal is you must drill then. So you do a small exploration well to confirm your assumptions from your desktop studies. Confirm that the rock is what you think it is. Confirm that the temperatures are what they are, or that you thought they were. Confirm that the stress zones and fractures and faults are behaving in ways like you expected them to behave. And then you test. So you drill a series of what we either call exploration or confirmation wells, and then you start flowing water through and you start taking measurements. How hot is this? Does the flow support what I thought it was? Is the system the way I thought it was and modeled it? And then, and only then, in the traditional geothermal sense, did you have an assessment of how much geothermal, where this place that you drilled, you could produce from that area. Now, this has been problematic because that's actually a pretty long process and quite a bit of capital before you're able to actually say whether or not you have a viable energy resource product, which can be tricky. So that was another thing that was hindering traditional geothermal development. All right, let's talk a little bit about bits. This is, again, not my expertise, so I'm going to speed through this one, but I do think it's really interesting because it leads to a little bit deeper understanding of why now we can drill in more places than we used to be able to drill economically. The oil and gas industry has spent the last decade plus in really perfecting drilling techniques and methods, driven primarily by the economic boom in shale and natural gas. Wherever you have money and infrastructure, or money and investment, usually innovation follows. Being here at Stanford, I'm sure that is not news to you all, but where there was money, the innovation followed in the drilling space. And some of these key innovations were things like changes in the drill bits, the cones, all kinds of different things. And it turns out that drilling for geothermal is very, very similar to drilling for natural gas. Another key element that I'd like to mention about geothermal, and once you have this resource, one of the things that you need in order to have a viable energy product is you do need the legal right to develop it. And that's something that sometimes if you're really focused on just the cool science, you forget. And it's a key element of why certain technologies will deploy faster than others. And in geothermal, it's a complicated picture because there weren't very many projects being developed. Geothermal itself can be either considered a mineral or a water, depending on the state or location here in the US, and actually internationally, it's even more complicated. Depending on how it's considered, sometimes obtaining the legal right and access to that resource can be tricky. So that's one of the ways that it is different than oil and gas. Typically, everyone understands that oil or gas is a resource or a mineral, and they will have those. Let's talk a little bit about that point that I mentioned earlier when I said that depending on what type of resource or the type of power plant that you use to convert this heat to electricity, that this resource can be either renewable or semi-renewable, and can either be fully carbon-free or have some carbon emissions. It can have air emissions if you use a particular type of power plant equipment on the surface. And typically this is associated with higher temperature resources and what we call flash or steam power plants, which I'll go into a little bit more later. But those types of facilities, because you can be bringing up elements that exist within the Earth's crust already naturally and vetting them into the atmosphere, you may have some fugitive air emissions. So these are some of the elements that in those types of geothermal you may experience or see. So you can see that depending, you can have some particulates, carbon dioxide, methane, sulfur dioxide. Important note here, though, is that the primary growth area of geothermal is in what we call binary cycle. And that is truly zero emissions and carbon-free because there is a secondary working fluid and the geothermal hydro fluid is never actually exposed to the air. I'm going to skip through this. Let's just say permitting is complicated. Thank you to whoever referenced the approval of Fervo's largest project to date, which is actually just last week. We had the approval of a 2 gigawatt, and you did hear me right, 2 gigawatts facility in southern Utah approved through the federal government. Super excited to be able to say that out loud. So we've been working on it for a long time, but that will be, essentially a giga geothermal hotbed there in southern Utah. And now it's completely approved. It's in construction at the moment, and over 500 megawatts of that is already under power purchasing agreement. And actually, with many utility providers here in California, we're sending a lot of that electricity here. So I hope that I'm around long enough to give this lecture in 2026 when the first phase of that project will come online, and I can say that the lights are being powered by geothermal from Fervo's projects. But that is tricky and something that needs to be worked on because depending on where you are in the US, geothermal permitting, the same exact well can be studied up to 6 times. So this is something that we've been working very actively with local and federal legislation on. Okay, I've mentioned a couple times Dry, flash, binary. Okay, let me make this really, really simple, break it down for you all so you can know what I'm talking about. Okay, we're talking about how we've just gone through very, very briefly how we find the resource, how we look at it, how we drill for it. Now we want to take that heat, create electricity. In the industry, we have essentially 3 different types of ways that we can do that. And we choose that type based on the temperature that we're targeting or find in traditional hydrothermal systems. Based on that's how we choose which of these methods we will use. And so if we start here from the lowest temperature resource, usually we'll need to use something called a binary organic Rankine cycle system. For the mechanical engineers or process engineers, you'll understand why, but that's because we need that type of system to exploit the moderate temperatures, usually between 212 F and 100 or 100 C. That's kind of where the target range that we're looking for there. We need that type of equipment in order to efficiently extract the heat. And what we do here is we use a separate working fluid. We run it through an organic Rankine cycle system, cool the water back down, and then re-inject it into the systems. Moving up in temperature, if you find a higher temperature resource, around 360 Fahrenheit or 182 Celsius, you can use what you do as flash steam. And this is because at that point, the resource is so hot that it's actually partially steam, right? It's not just within the water and your working fluid, so you need to use different processes at the surface. That's where you may have some of these fugitive emissions. If you're flashing some of the steam and there's naturally occurring sulfur or other elements, some of that may be released into the atmosphere. Similarly, if you move up even more in temperature, you end up with maybe only steam coming out of the ground. And in that case, if you're somewhere between 455 F or 235 C, then you're going to need to use even different processes, and you may use that steam directly for power production. So it's the temperature that really determines what type of power plant you're going to stick on the surface to exploit the heat and turn it into electricity power production. I like this slide because for those of you that are visual learners like myself, it kind of re-emphasizes the difference between these. So again, kind of moving from left to right here, we have the dry steam plant, and you can see in this scenario, you're just bringing that dry steam up, you're putting it directly through a steam turbine. You're using that turbine to turn a generator. That creates electricity. A flash steam plant, you've got 2 processes where you're dealing with both the heat that's within the fluid, the water that you're bringing up from the facility, as well as the steam. So you're sort of separating both. And then you have a binary cycle plant, which is essentially just bringing the fluid up, moving that through a heat exchanger, using your heat exchanger and to have your working fluid turn your turbine and generator for electricity. So those are the 3 ways that it is generated electricity. So where's the growth? The growth in this industry is almost exclusively in binary cycle. It's for a couple of reasons. It's cheaper and easier to access lower temperature resources usually. And also because, as I saw in the beginning of the lecture, if you remember, most of this growth is being driven by the desire to fully move to carbon-free electric systems. So if you want to do that, you probably want to have a fully carbon-free way of converting this heat to electricity. So this graph just shows essentially the US geothermal capacity by plant type. And you can see that there's this big green or this big blue section at the bottom of this graph that is all the dry steam, and that is actually almost exclusively the geysers. This is actually a massive power plant. Maybe if you've been studying other energy resources, this number may not seem so big to you, but the geysers was originally almost a 2 gigawatt plant, which for an industry where like globally, that is essentially 3/4 of the overall installed capacity worldwide. It's kind of blows your mind when you really think like, so when your teaching team says to you, you have an opportunity to tour, you're like in the heart of geothermal. If you really are interested in this resource, like make the time, go see it. It's really, it'll something that not many people in the world get to see, and it really is like a piece of history of geothermal. But above that, you can see is a little bit of single flash, and then you got double flash, and then most importantly, you can start to see that resurgence in the early 2000s of binary. Again, graphical form of the heat. Okay, so dry steam is the easiest form of production, I would just say. Little mention here. It's very limited because it's really close, as we're literally just got steam coming up from the ground, and so it is the easiest. And I think, you know, one of the places to look is we see this in Indonesia. So for those of you that are a little bit more interested in international expansion, this is, you know, one of the growth sectors there. They've got a lot of dry steam plants either in operation or in development there in Indonesia. Flash steam plants, today currently the most common because it has a combination of both. Although I actually think that this is changing. I think we need to, I think I need to look and make sure that this truly is the most common. We might have hit a tipping point here where very soon more installed capacity will be binary than flash steam. And then binary cycle. Again, these are here within your slides so that you can go through and download if you're very interested. It's a small world capacity. Interesting place where there's been a lot of growth in binary cycle is actually within Turkey. There was, and now the United States, obviously, we will clearly surpass them in installed binary capacity in 2026. But up until then, Turkey was the highest growth area for binary cycle plants. Let's see, new installations in the US. This is an interesting fact here to just kind of quickly look at some of where the new installations have been. We have, you know, as of 2020, the US has 93 binary cycle plants, which is about 8 megawatts on average a piece, and 79 steam generators. So, you know, California for sure is the by and far and away the leader. So you are in the right place to study geothermal energy. I had an interesting conversation at breakfast with some of the students about some of the ways that some of the innovations that are occurring, and this is one of them. So some new plants are combining flash and binary cycles together, as well as with some interesting solar radiation. So that is something that I would encourage you all to look at. Another thing that is happening is that this slide is actually here because you can essentially subvert part of the cycle of an organic Rankine cycle binary plant and essentially have that plant act as a load following facility, much like a combined cycle natural gas plant. And there's one instance in operation of a plant that actually operates this way. This is the Puna site on the Big Island in Hawaii. And actually the site of the geothermal convention that is happening here this week. But this is really interesting, and I mention it from a market perspective because as we are firming renewable intermittent power, applications like this, where geothermal can ramp quickly and also turn off when there's lots of wind and solar on the grid, are becoming an increasingly important part of the value driver for geothermal energy deployment. Okay, so a little bit of where is geothermal resource? In the US, it's typically in the western United States, or where it's accessible at lower depths, 7 kilometers deep. This is a map that shows at least in a demonstrative way where temperatures are at 7 kilometers, and you can see that it is localized in the US. This is a lot. I told you we were just going to keep going. I'm going to keep powering through. I want to talk now that you understand about the magic trifecta you would have to have for traditional geothermal, the where it's typically at, and also you know, some of the limiting factors. I want to talk now about an interesting elements of what's happening from a technology perspective that is helping to accelerate the deployment of geothermal. And one of those is enhanced geothermal systems, or hot dry rock. And this is where companies are using the actual system itself without water necessarily. And it's interesting, but it can still be a little bit tricky in terms of the overall economics, because you still have to think of it in the broader development context. You can, from a technology perspective, hot dry rock is really super interesting, but you also have to consider geothermal development in terms of its overall process. You have to have the economics and the financing and the interconnection all at the same time to make sure that it's going to work. We're going to watch a fun video, and when we come back, we're going to talk about the market and further about how all these things come together to either accelerate or not the deployment of geothermal.
Alaska has more geothermal energy than all the states put together. But yet Chena Hot Springs is the first geothermal power plant in the state of Alaska. Now this power plant is making power off of water that's not as hot as McDonald's coffee.
We developed lower temperature technology, so you don't have to go after 300 or 400 degree water or steam.
This is working. We're doing it. I mean, the lights are on right now geothermally. Now we're going to enter the largest ice structure in the world to be up all summer. Now, Forbes magazine voted this the dumbest business idea of the year. Mr. Forbes can kiss my ass. This entire structure is kept cold geothermally. It cost me about $12 a day to refrigerate this place. If you did it on diesel fuel standard, it would be $750 a day. It's the cheapest thing going. Our electricity was costing us 30 cents a kW. Right now, we're at 5 cents a kW. In 3 to 4 years, we'll be 1 penny per kilowatt hour. We'll have the cheapest energy in the state of Alaska.
One of the reasons I like Bernie so much, I mean, there's so many good things in that. I can't wait in 2026 to be like, the lights are on geothermal. I want to steal Bernie's quote for us, geothermal power. But one of the other things I really like about what he says is he really highlights the fact that geothermal, if you think about it from many ways, is bipartisan and can really make sense for no matter what. And it actually is helping to put a lot of the oil and gas workforce is directly applicable to some of the greatest innovations in geothermal. And so on the screen is my quick brag moment, this is Emma. Emma works at Fervo. She is an amazing geologist, one of the most interesting people that you will ever take a hike with, because she will say things to you like, in the recent history, 5 million years ago. But she's also an ex-oil and gas worker, and she spent the first few years of her career using those amazing geology skills to exploit and bring oil and gas up from the surface and kind of contributing to climate change. And we hired Emma on, and she is the principal geologist and reservoir modeling engineer on our project in Cape, which we just said will very soon be contributing 2 gigawatts of clean, firm power to California and the US beyond. And I just think that that's such a cool story for so many reasons, because she's doing exactly what she loves to do, what she was trained to do in the oil and gas sector, and she's using it now to be part of that solution. And it makes economic sense, puts money in their pocket, like Bernie says. So geothermal energy, still small picture of the world's component. I said earlier, less than 1%. I did mention some of the growth key areas, but since I've got time to mention it, I think it's really interesting to actually talk about Kenya here, which is a surprise geothermal star. So in Kenya, actually, if you look at the overall installed capacity of all energy resources in Kenya, by far and away the largest portion of generation type that they are using in Kenya is geothermal, which is like kind of bizarre. And you're like, why Kenya? It was bizarre to me. It's like, why this like random African country has figured out geothermal and we haven't? It's partially location, where they are located, but there's other countries that are just as advantageous from their location that haven't actually deployed as much geothermal. And the reason turns out to be the way that they have addressed this intersection of policy, resource, and financing in Kenya. Kenya did something really interesting where they used private-public partnerships, where they used public dollars to help de-risk a geothermal resource, which now, through the course of this lecture, hopefully you've seen why that's so important in traditional geohydrothermal. So because they used private dollars to tell people where exactly the good geothermal resource was, and then they used public dollars to do that and then let private developers go develop those resources, it worked out extremely well. So there's some lessons to be learned there from Kenya. Direct heat use of geothermal it does meet a small portion of the heat needs. We already talked a little bit about where it's growing. It is growing in China. We didn't talk about some of the industries. I'd say, 3 industries to highlight where geothermal heat for direct use is growing and in popularity is in agricultural recreation and public works, particularly in public works, as we're seeing agencies and others trying to green essentially all elements. I heard you guys talking about the buses here of EVs, places where there's a lot of high temperatures or low temperatures are equally trying to figure out how can we do this smarter, and geothermal for heat production as well as public sidewalk heating and things like that is one place where they're growing. China is the definite, by a lot. When we say growth sector, not a little, but by a lot. Essentially this is just a massive growth industry there, and in some ways where I can't even hardly keep up with some of the deployments of geothermal for direct use in China. Obviously it's a heavy manufacturing hotbed, but I also think that highlights a key thing about this, which is that done right, it is economic. And yes, China is moving towards geothermal for direct heat because it is sustainable, but more so they're actually finding it also has energy security and cost savings as well. So it's interesting. Okay, so let's look about the mix. We mentioned some of these numbers ahead of time, but yeah, still fairly niche. This just gives you an idea of, how geothermal compares to the rest of the energy industry in terms of installed capacity. It's still pretty small. I mentioned that the US right now has 2.7 gigawatts of net generation capacity, 3.9 nameplate. That again has to do with the decline of the resource. So ability to generate up to 3.9, but really what is being generated is 2.9. However, the more interesting thing is to look at how much is being deployed year over year comparatively. And you can see that in 2002, 80 megawatts was deployed, and that 2 gigawatt number now, when we talk about permitting a 2 gigawatt facility in Utah, maybe now it's clicking why this is newsworthy and why Forbes is talking about this and all these other things people are talking about it. It's just because comparatively that's a 100% year over year growth in the industry. There it is in graphical form. Probably noticing a theme. I like to show it in words, show it in pictures. So if you're more of a graphical person, you can kind of see how this is stacking up against other renewables. The United States maintains its commanding lead in installed geothermal capacity, although the new capacity built has averaged 66 megawatts annually from 2011 to 2021. Only 25 megawatts of projects were completed in 2022, which helped keep the total net operating capacity to around 2.6. So it's a base load resource. Geothermal is what you may hear it called a base load, and what we are talking about there is we're talking about its overall capacity factor, meaning it does generate all types, whether you're talking about dry, steam, flash, they all generate at a high capacity factor. You might be wondering, why is that not 100%? And the answer is thermodynamics. We have now learned that the vast majority of the growth is in the binary cycle systems, and in particular in air-cooled binary cycle systems. So you saw through those graphs and figures that essentially what we're doing is we're bringing the hot fluid up to the surface, we're running it through power production, and then we're injecting the fluid back down into the reservoir. We have to cool that fluid a little bit. And when we say air-cooled, we're talking about just general air-cooled condensers like you would use on a natural gas plant. And those air-cooled condensers are less efficient when it's hot outside. Really, just simple physics here. And that means that a binary air-cooled system produces a little bit less power in high heat areas. And now, this is really interesting though, because now I can talk about one of my favorite things, which is the complementary nature of how binary cycle air-cooled systems are fitting with some of the other renewables that we have widely deployed. So you guys have seen this, I think, at this point in this lecture. So this is the California infamous duck curve. And what we see here is that when we have large percentages of solar on the grid, we're seeing extremely negative pricing in the middle of the day, which coincidentally is exactly when it's hot and when geothermal produces a little bit less power inherently. So the point of this is just to say that there really is a complementary nature to the highest rapid growth sector of geothermal energy plants that are being produced with problems that you inherently see as higher percentages of intermittent resources get deployed on grids. So it's a very complementary thing to be developed along with additional wind and solar in a grid. This is bringing us all the way back now to the beginning of the lecture, where I talked about the midterm reliability decision in California. This is one of the reasons why I think the first version of that proposed decision by the Public Utilities Commission was written as a geothermal procurement mandate because of this complementary nature and as well as the fact that it is clean and truly GHG free. So they required that, based on their projections of both energy use and demand and the retirement of Diablo Canyon, that they would need 11,500 megawatts to keep the grid reliable. And you can see that at least 1,000 of that was to be procured from these clean, firm resources. A very important piece of legislation. So worldwide, geothermal electricity capacity is adding less than a gigawatt a year. Again, just one more context point here for if you've got a 2 gigawatt project that's now approved and worldwide you're deploying less than a gigawatt per year. You can see the massive inflection point in this industry. Also here you can see some of the key areas of growth there in Kenya, talking about how in Kenya is 48.4% of their total electricity generation was generated by geothermal energy in 2021. Also, people inevitably ask, okay, so Dawn, you've been talking about how it's more economical in some places, not economical in others. What does that really mean? How does that compare to other resources? Well, let's use LCOE. As a developer, it's my least favorite way of talking about the cost of resources, but I will use it because it is the best we have and no one has come up with something better. So we'll talk about it, but the LCOE right now of geothermal, if we use publicly available data, is shown there in comparison to the rest of the resources. So you can see that it's sort of like middle of the pack. There are definitely cheaper resources. I said earlier in the very beginning part of the lecture that if you are a person who is charged with totally greening your grid and you have to choose between your resources, you're going to fill up with wind and solar first, and this is why. Because the overall dollar per kW installed of that resource is going to be cheaper, so it's going to be cheaper for you to install, but you cannot fill your entire grid and end up having 100% with renewable electricity without adding some other things. And so if you add geothermal, it is likely that you will end up in a least cost best fit grid that is totally carbon free. And we're seeing that as utilities are working through what they call their integrated resource planning, where they're doing these long-term looks of what types of supply I need. They do these very big complicated models, they put in these LCOE numbers, and what we're seeing is that when you impose the constraint of having to be totally carbon-free by a certain point, that essentially these models are choosing as much geothermal as possible. And that's why you have companies talking to Fervo about 2 gigawatt plants in southern Utah. Okay, so another important point is that legislation really matters, and regulation and support and financial support really matters for deployment of resources. So you can see here the impact of federal tax credits on the levelized cost, and you can see that they do have an important impact, not just for geothermal, but for all resources. So this is an important key part as well of launching any renewable development into its full potential. All right, let's talk a little bit more about growth and where we're going. So growth really has just started to accelerate, and you can see graphically here where it's going. You can kind of start to see those trends when we look at both from a global and domestic perspective, just how quickly we're starting to rapidly deploy, and also you see that sort of periods of stagnant growth in the early sections. Also, future of geothermal heat, we do expect will continue to grow in China. And internationally, although I probably need to start updating, as I was talking with some of the students earlier at breakfast, as we're starting to see higher and higher geopolitical instability and people being more and more interested in energy security, we are starting to see even more international interest in geothermal as a secure, localized, stable form of carbon-free energy. But in the future, we will still see that worldwide, it will probably still be a relatively small percentage of the overall energy mix internationally, but it could change. So there are some interesting co-location elements for geothermal. One thing that is happening in this space is that because of the inherent nature of the processes of converting thermal energy to electricity use, there's a lot of interesting like co-location things that are happening in our space. One of them is direct air capture. Turns out geothermal is a really interesting from a technical perspective to use for direct air capture because you can utilize the subsurface system to capture a carbon at the same time as you're using the electricity for that capturing process. So these are inherently very complementary systems. So there's some interesting work there happening with the Orca plant. It's the largest direct air capture plant. It's started operation in 2021, and it's located in Iceland. So that's an interesting fact there. Also here locally in the state, there are some companies that are working on co-locating geothermal with mineral extraction, particularly lithium. So we have a very high lithium deposits in a typically active geothermal space here in California, in Southern California, in the Imperial Valley. So there's some plants and facilities and folks that are using that as an additional value stream to help with the economics of the facilities. Let's talk about Ever for a second. Ever is doing something really interesting as well in terms of geothermal for pumping free and in areas where potentially creating additional fracture zones are not necessary. So you now know that magic trifecta where you need sort of those three things. Ever is using sort of like a closed loop system in order to do deep geothermal in highly populated areas. It's some interesting stuff, mostly being deployed in Europe. Interesting economics, but certainly in particular areas. Also at breakfast, I was talking with students about like not one of these solutions is the magic bullet. And I think if you took away one thing from this part of the lecture, I don't want you walking away thinking like, even though I'm from Fervo and I, of course, believe in the system that we are developing, we require all of these innovations in order to actually use geothermal energy in its maximum potential, because everyone has its own particular unique place where it makes the most sense. So geothermal, actually, at the moment, the leading developer is actually Ormat. They're still by far and away the largest binary cycle developer. They have 190 plants worldwide and are continuing to be an active development. They do develop traditional hydrothermal resources, and so their development pipeline and growth over year has been fairly limited, but they've been one of the companies that's successfully navigated all of those challenges that I put up in that kind of confusing form of like how interconnection and permitting and all these things have to intersect in the right way. They've been very good at doing that. Now moving on to Fervo. And I said Fervo and then started with Forge. So you're probably like, what the heck? But it's because Fervo is actually really taking advantage of a really unique private-public partnership and advancements that the Forge project, which is located in southern Utah as well, just a stone's throw away from our now commercial site, Cape Station, they were the first ones to actually do what we call advanced geothermal, where we take that naturally occurring trifecta and remove one of the elements and essentially say, what if we didn't have to find perfectly porous rock? And instead, all we had to do was drill to the heat and have a water source. And we could create and engineer the porous system, the reservoir system through which the water can flow. And that, at its fundamental, is what Forge proved. They drilled down, they drilled horizontally, and they proved that this was possible. And Fervo simultaneously was doing our first commercial project in northern Nevada, and now is taking a lot of the data and a lot of the resource that was developed publicly. Maybe you're seeing some themes here to what Kenya did, and is turning that into a private and successful project that's being deployed commercially. And so this is a graphical representation of what Fervo does versus traditional hydrothermal if you aren't used to it, but this is what we do. Is, on the left-hand side is a traditional hydrothermal binary cycle. You would find that heat source, you would drill, and you would drill a series of many wells, but usually one producer, one injector, and you would just drill down and try and find a naturally occurring fault system where you have connections between those two. And you would pump cold water down into one area and bring the hot water up through the other. Then you would extract the heat and put that back down into your system. The problem is that traditionally, these wells are very expensive, $4 million plus for every single well, even today, that you're going to drill. And you have to find everything just right, just perfectly. And if you don't, you end up with what's called a dry hole. So Fervo was founded on the principle that if we removed the dry hole risk, we could save a lot of money up front. So we could do this more economically, meaning we could drill to higher temperatures, lower in the Earth's surface at the same price. And we could actually also control through engineering controls better our flow and other elements if we had some control of how the water was moving between the injector and the producer. So what Fervo does at its basics is we drill an injector and a producer, but we also utilize horizontal drilling that was developed in the oil and gas sector, and we use completion techniques where we actually create the fractures within rocks. It's different for a couple of reasons. We're actually trying to avoid naturally occurring fault zones, which means we have a slightly lower seismic risk than traditional geothermal. And we are better able to control and essentially drill to our exact flow and temperature. It's been a really interesting experience as I have been negotiating and dealing with traditional power plant developers. So I go to these sort of like ORC vendors who are used to waiting through all that process, and then they say, okay, tell me your temperature and flow your wells are giving you. And I'm like, and they're like, what do you mean you haven't drilled everything yet? And I'm like, well, I don't need to. I'm going to drill the system to be that temperature and that flow. And it like blows their mind, because typically it was every single geothermal facility was this bespoke thing that was developed for the resource you found. Now you're sort of engineering the resource to your optimal power plant on the surface. So you can see how that would lead to more rapid and lower cost deployment. Also really interesting things being done in deep drilling. Thank you all so much for your time and your attention and your interest in geothermal.